But if we want to find the partial half-lives, the partial half-lives are always longer than the true half-lives. It's kind of almost like a misnomer calling it a partial half-life, because partial sounds like it should be smaller, but it's really a bigger number. So the number that we got doing the math was 12.701 hours. If we wanted to find out, but that was something that we got for the overall actual half-life. But if we wanted to find out for electron capture, what we would have to do is then divide that number by the percentage of this that's electron capture. Electron capture was 43.57%, so expressing that as a decimal would be 0.4357. And once we do that, we'll actually find out that we're going to get a number, a half-life that's going to be 29.15 hours. So that is for electron capture. That would be the half-life for electron capture. So we're actually able to use that to take the overall half-life and then look at the different partial half-lives, and we actually come up with we can use that number to actually determine what the partial half-life for electron capture is, what the partial half-life for positron decay is, or anything else for that matter. Okay, starting to get late here, so I think I'm going to just do one other thing here. I'm not going to cover, there's one section in here about statistics. That won't, well, I don't know. Let me see how much I can do. I don't know if I'll actually have enough time to do that. I might have a few minutes. But I want to talk about equilibria, because that is also important. When we've got one element decaying into another element, if depending on, we start out the element that's doing the decaying, we call that one the parent. The one that it's decaying into is the daughter isotope, or the daughter nuclide. So we have a parent nuclide decaying into a daughter nuclide, and if the half-life of the parent is much longer than the daughter, what's going to happen is we isolate pure parent, and let me draw this here. If we actually isolate the pure parent, and we have time on the x-axis in terms of this is measured in half-lives. So we have 1 half-life, 2 half-life, 3, 4, 5, 6, 7, and then on the y-axis, we're going to measure activity. Now, we're going to start out with some pure radionuclide that's going to be decaying into something else. And this one's going to have a very long activity. Could be something like uranium-235, which is hundreds of millions of years, or it could be uranium-238, which is 4.5 billion years. So it's going to have, over the time period that we're going to be observing it, it's really going to be, it's really not going to change. So we're going to see kind of a straight line relationship here for that. And then what we're going to see, this is actually daughter half-lives, not parent half-lives. Obviously the parent does change, but in terms of daughter half-lives, over that period of time, since one is much longer than the other, this one is not going to change. So the daughter is going to start out at 0, because if we isolated and purified this one nuclide, it hasn't even had any time at time 0. At time 0, there's not going to be any daughter. But then the daughter is going to gradually, let me use a different color. The daughter is gradually going to increase. And she's going to come up like this, and then eventually she's going to get to the point, after we go to 1, 2, 3, 4, 5, 6, 7, right about here, she's going to get to the point where she's not going to change anymore. At about somewhere around 7 half-lives, the daughter and the parent are going to have about the same activity, and we're going to get this straight line relationship that's going to go on and on like that. And if we were to look at the overall activity, we would start out here. This is flat, but if we're adding both of these up, then the overall activity is going to be somewhere up here like that, and it's going to have about the same shape as this. So that's when we have that kind of a situation. Once we get to the point where these two things appear to not be changing anymore, we call that equilibrium. And it's not the same kind of equilibrium that we talk about in the chemical sense of equilibrium, where we've got a forward and a reverse reaction, and they're both occurring in such a way that the things that are in equilibrium remain constant. This is, radioactive equilibria are quite a bit different than that. But in this particular case, where we've got parent, very long half-life, daughter, considerably shorter half-life, we call that secular equilibrium. And we also have another situation, and there's a problem here that you can see on page 28, an example where we're trying to find the half-life, and it's a secular equilibrium type of problem. We have a couple other equations, which again I would give you. One of these is the n sub b, which is the number of atoms of B, the daughter, divided by the number of atoms of A, the parent, is going to be equal to the half-life of B, the daughter, divided by the half-life of A, the parent. So we can use those kinds of relationships to calculate a half-life if we know how many atoms of each of the parent and the daughter are present, and we know the half-life of one of the two isotopes. We can find that of the third one. There's something else called transient equilibrium, and it's very much like secular equilibrium in that the half-life of the parent is longer than the daughter, but it's not so much longer. So what's going to happen in that case is, in the time that we're actually observing it, this is going to start to fall off as well. So it's going to look very much like this, except, and I'll call your attention to the graph on page 30. What's happening now is that this line is falling off with time. So this line actually now is decreasing with time. It's going down slowly. And what's happening is this one is coming up, but then it starts to go down as well, and still follows this along. So when we see this kind of occur, and then of course this is going to look the same way up here, it's going to come and then it's going to start to fall off as well. So when we see that, we have what is known as transient equilibrium. And we're going to use a similar kind of equation, which is this. Before we had NB over NA equaled T1 half B over T1 half A. Now we have NB over NA equals T1 half B divided by T1 half A minus T1 half B. Because what we have to do is we have to correct for the amount of T1 half, we have to correct for the half-life of B that's in our denominator. And you can see that's done in the example on the bottom of page 30. So hopefully you can, the math on these things are fairly straightforward, and you can see how that's done. But the idea is just to show you these two different kinds of equilibria, that is the secular and transient equilibrium. And there's a third case as well, which is where no equilibrium is established at all. And this is a case when the parent the parent's half-life is actually shorter than the daughter's half-life. Then it's impossible to have equilibrium. But you can still use the same kind of equation that we used, an equation very, very similar to the one that was shown previously. And there is an equation shown on page 32 where we can find, what we can do is we can calculate the maximum daughter activity for transient equilibrium and use that same equation to find out the maximum, the time where we're going to get actually the maximum concentration of daughter. So T sub max, this is on the top of page 132, is 144 times T half-life of T sub A times the half-life of T sub B divided by half-life of T sub A minus the half-life of T sub B times the ln of the half-life of T sub A divided by T sub B. So that's those are all of the equations that you use for doing these things. Now there's one other thing. I've gone almost an hour, so I just want to talk about this very, very rapidly because I know I went way over an hour. I told you I would try to keep it down to an hour, but we've gone just about an hour now. But I do want you to at least look at the sections on statistics here, and the things that I would like you to be aware of are the fact that there's something called a standard deviation, which is approximately equal to the square root of the mean. Actually, if you have a very, very large, if you're taking a lot of readings, and this is using count rate as an example. So we're looking at something that was radioactive and we're counting it for a period of time. I think it's maybe it's 30 seconds of counting. I'm not really sure what they. I guess it's a minute. They're counting it for a minute, and you're counting it. You count it, and then you're counting it again. You're counting it again, counting it again, and you're getting these different numbers. And you want to look at the numbers and say something about the statistics of the numbers. So this is the table on page 33, table 2.3. So you look at all these count rates here, and what you find is that there's a fair amount of variation in there. What we like to be able to do is express this in terms of something called sigma, or the standard deviation, and it's actually the square root of the mean being the average of all these values. And when you do that, what you'll see is that for radioactive decay, which is a random, or the other word you should know for this, which you'll see, I don't know if your book uses it, but we call it these are stochastic events. Stochastic is another way of saying random. So when you've got these kinds of random events, we know that a certain amount of a radioisotope is going to decay in a particular period of time, but we don't know, we can't say anything about any specific atom. We don't know when that particular atom is going to decay. We only know that over that period of time, half of the material that's in there will decay, and then over the next half-life, again, another half of what's remaining will decay. So what we can do is we can actually look at all these decays, and what we expect is that this should establish something called a Gaussian or normal distribution, which looks sort of like this. And what we can tell from this is, using these standard deviations, is that this is the mean right here. And we can tell from how far we are, any particular value is from the mean, we can get an idea. Other kinds of things like IQ fall in this same kind of a distribution, a normal or Gaussian distribution. So when you have that kind of a distribution, we know that 95.5%, well, we know that 68.3% of all of the values that are in here will fall one standard deviation from the mean. So that would be 68.3% will fall, I went too far over here, one standard deviation from the mean. So that, let's say that's about right here. So from here to here, that would give us 68% of all the values. And then if we went over a second standard deviation, the two standard deviations from here to here, then we would actually encompass 95.5% of the values. And if we went to three standard deviations, which takes us out to the tail, we would be at 99.7%. So generally, for most of the work that we would be doing, we'd like to look at plus or minus, we'd like to be within two standard deviations. So what we can do is we can look at some other things in here. We can actually find something called the standard deviation of the mean, which is useful if we're actually trying to, if we take the normal standard deviation, the one that we just calculated before, and we divide that by the square root of n, which is the number of determinations we made. In this case, in the previous example, we found that the sigma, the standard deviation, was 46, and n was the number of data points was 20. That's 46 divided by the square root of 20. So the standard deviation of the mean would give us 10 counts per minute. But there's also something called the relative standard deviation, which is the standard deviation divided by the mean, and that comes out to be 0.022. So you should know some of these definitions. There's only one other thing in here. I have to talk about this real fast because I'm going very, very late now. And this is the chi-squared test. It tells you, your book tells you that even though we're saying these things, that radioactive decay is actually a normal distribution, there's something that's very, very close to that that's called a Poisson distribution. And they're saying that really radioactive decay can be approximated using a normal distribution, but a Poisson distribution gives us an even closer, it's not an approximation, it actually is a Poisson distribution. So you can actually, what you can do is you can actually plot, we saw these plots before where we plotted the natural log on the y-axis and time on the x-axis, and we saw that it was a straight line, and you can see that there's a line, there's a plot on page 37 that's actually showing you time, and it shows you every one of those 20 points. But there are error bars that look like this that are established for the points. And those error bars are, I believe, plus or minus 2 standard deviations. So that's what that means is that as time gets longer, the error bars get longer. So as we go down to longer and longer times, but you can notice that those error bars are getting greater and greater. But these points, they're not going to all fall right on a line, but they will approximate a straight line, but they will all fall within, the point will be somewhere on the error bar in here. And then we can just use, there are computer programs, or those of you that know how to do linear regression can fit those points to a straight line. You won't be asked to do that, of course, on the exam. But there is something here to determine whether the data set actually follows a Poisson distribution. You can calculate something called the chi-squared value. And chi-squared is equal to 1 over the mean. So chi-squared equals 1 over the mean, that's x bar, times the sum of all the values x bar, which is the mean, minus the individual value, the square of that. And when you add all these up, for instance, for this particular set of data, it tells you that the chi-squared value is 14.9. I just want to call your attention to the fact that there is a table in here. If I can find it, it's in the back of your book. It's on page. Bear with me for a second. It's in the appendix, I think. Yeah, here, I just saw it. It's on page 237, Appendix C. It's a table of chi-squared, and the probability of observing an outcome at least as large as the chi-squared value. And what you do is you notice there's something on the left-hand side that's called degrees of freedom. That is going to always be 1 less than the number of observations that you made. So there were 20 different sets of counts that were made, so the degrees of freedom would be 19. And if we look across there at 0.5, we're going to find, actually, no, we don't want to look at 0.5, we want to look at 0.9, which is going to be plus or minus 0.05. It's actually going to be about 1 standard deviation in either direction. We're going to get a value of 11.65, and you notice that our chi-squared value was 14.9. So it's right in that area. It's right in the correct area. So there's a lot of math in here, and I think I'm more concerned. You know, I said I'll give you a few math problems, but I'd like you to really know the definitions of things like secular equilibrium, transient equilibrium, and some of the other defined terms, particularly the things that are in bold in this chapter. This is the most mathematical chapter, and everything after this will seem like a piece of cake.